This is Convex Influences, and it's joint work with Anindya and Rocco Servedio. So at a super high level, this talks about an emerging analogy between monotone Boolean functions on the n-dimensional hypercube and symmetric convex sets over Gaussian space. So just to remind everyone, the n-dimensional hypercube is just a collection of 0, 1 strings of length n, and a function is said to be monotone if flipping an input bit from 0 to 1 cannot cause the value of the function to decrease. And we say that a set in Rn is symmetric if it's symmetric about the origin. Or more concretely, if a point x is in the set, then the point minus x obtained by reflecting through the origin or flipping the sign of each of x's coordinates is also in the set. And over the past few years, many structural and algorithmic parallels have sort of been discovered between these two settings. And this work in particular explores a new notion of influence for symmetric convex sets. So I'm going to first start by sort of very briefly describing some of the background and some of these parallels that people have discovered between these two settings, after which I'll spend some time talking about a specific point of correspondence between monotone Boolean functions and symmetric convex sets. And this point of correspondence is actually what led us to this new notion of influence. So monotone Boolean functions are very natural class and have been extensively studied in combinatorics and Boolean function analysis and learning theory and property testing. In particular, a lot is known about their analytic structure, low degree concentration, about learnability under the uniform distribution, and so on and so forth. But a lot of these themes have also been studied for symmetric convex sets in over Gaussian space. Of course, you sort of replace the uniform distribution with the Gaussian distribution, and you replace the Fourier transform with the Hermite transform. But despite this, a lot of the results are still, there's a very clear correspondence between the results for monotone Boolean functions and the analogous results for symmetric convex sets of a Gaussian space. And one sort of point of correspondence which makes this analogy very clear, in my opinion, is that of correlation inequalities. And this is sort of what led us to this work, as I just mentioned. So the Harris-Gleitman inequality informally says that any two monotone Boolean functions on the n-dimensional hypercube are non-negatively correlated with respect to the uniform distribution. And this is sort of a well-known, well-studied inequality, which has lots of applications in combinatorics and statistical physics. It's also been known for a while. It was discovered in 1966, and its proof is a 5 or 6 line long inductive argument, so it's not too difficult. On the other hand, in the setting of symmetric convex sets of a Gaussian space, the analogous statement is simply the fact that any two symmetric convex sets are non-negatively correlated with respect to the standard Gaussian distribution. But this inequality, despite looking very similar to the Harris-Gleitman inequality, was open for over 40 years, and it was only proved in 2014. Another way of stating this inequality, which was proved by Thomas Royan and is called Royan's inequality, is as follows. It says that the Gaussian measure of the intersection of two symmetric convex sets is at least the product of the Gaussian measures of the sets themselves. So hopefully this sort of, maybe you're not convinced that there's a very concrete analogy between these two settings, but these two statements are very similar. One thing to note about both these statements is that they are qualitative statements. Or in other words, what they say is that there's the correlation between any two functions belonging to a certain family with respect to some distribution is non-negative. And a natural thing to hope for is a robust version of this statement. Or in other words, can we get a better lower bound on this correlation quantity? And ideally, we'd want to do this in terms of some property of the functions that we're looking at. And when you think about the Harris-Gleitman inequality, it's easy to check that you have equality in the Harris-Gleitman inequality when the functions f and g depend on disjoint sets of coordinates. And And so it's natural to hope for a lower bound in terms of how much the functions depend simultaneously on the same on a particular coordinate. And this notion of dependence on a particular coordinate is actually a very well studied quantity in Boolean function analysis, and it's called the influence of a coordinate on the Boolean function. More formally, if you've got a Boolean function f on the n-dimensional hypercube, you can define the influence of any of its coordinates as follows. The influence of a coordinate on the function f is the probability that when you choose a point uniformly at random from the Boolean hypercube, the value of the function at that point is different from the value of the function at the point obtained by flipping the ith coordinate or the ith bit of the original point. And this is a very well studied quantity, and there's been a long line of very interesting, very cool work built around this whole notion of influence. Returning to correlation inequalities, Talagrand in 1996 asked this very exact question, namely whether it's possible to get a quantitative version of the Harris-Gleitman inequality, where the lower bound is, some function of these influences. And Talagrand obtained such a bound in 1996, where he showed that the correlation between any two monotone Boolean functions is lower bounded by this function psi of the sum of the products of the influences. And Talagrand's inequality has found many applications in additive combinatorics and Boolean function analysis and elsewhere. So the story so far looks something like this. You've got the Harris-Gleitman inequality, which is a qualitative correlation inequality, and you've got an analogous statement for symmetric convex sets in the form of Royne's inequality. And then Talagrand comes along and robustifies the Harris-Gleitman inequality to get this expression, to get this really cool inequality, which lower bounds the correlation between two monotone Boolean functions in terms of the influences of the two functions. And it's natural to hope for an analogous statement in the setting of symmetric convex sets of a Gaussian space. And this is precisely what we obtained in some previous work last year. We showed that the correlation between two symmetric convex sets under the Gaussian distribution can be lower bounded by this function phi of the sum of the products of the degree 2 Hermite coefficients of the two sets. So these functions phi and c, they're off by a logarithmic factor, but that doesn't matter too much. What's really crucial for the purposes of this talk is that it looks like, just pattern matching, these degree 2 Hermite coefficients sort of seem analogous to influences. And motivated by this analogy, we define the convex influence along a coordinate direction as the negated degree 2 Hermite coefficient along that direction. If you don't know what the Hermite coefficients are, if you don't know what the Hermite spectrum is, that's totally fine. It'll all disappear in a second, and there'll be a clean and crisp definition of convex influences. But before I show you the definition of convex influence, one thing to note is that in Gaussian space, there's no canonical direction. So it's reasonable to hope for a definition of influence along any direction. And so given a symmetric convex set, you can define the influence of a direction on that set as this quantity, which is the expectation of the indicator function of the convex set times the negated degree 2 Hermite coefficient, Hermite polynomial evaluated along that direction. And this is it sort of looks like a weird, arbitrary technical quantity, but there's a significantly more intuitive way of thinking about these influences as follows. So given a symmetric convex set K, let's say we are interested in the influence along the first coordinate direction, E1. So this is just, E1 is just the basis vector, which has 1 in the first entry and zeros everywhere else. And you can sort of define this diagonal matrix where you sort of scaling your convex body by a factor of 1 plus delta in the first direction and leaving all the other coordinate directions unchanged. And I'm just going to denote this matrix M sub delta. And it turns out by a not too hard calculation that the influence of E1 on the convex set, on the symmetric convex set K, is essentially capturing how quickly the Gaussian measure of the set K changes under dilations when you dilate it along the first coordinate axis. And this sort of characterization of convex influence in terms of dilations is analogous to the Russo-Margulis lemma for Boolean functions, for those who know what that is. So at a very high level, the Russo-Margulis lemma tells you how quickly, how the bias or the volume of monotone Boolean function changes as you sort of varying the underlying measure. So as you're sort of changing the bias of the underlying measure on the Boolean hypercube. Or in terms of pictures, what the influence of the first direction on a symmetric convex set K is the limit of the change in the Gaussian measure of this new set M sub delta K and the original set K divided by delta as you send delta to 0. So it's sort of the rate of change of the Gaussian measure as you sort of dilate along the first coordinate direction up to some scaling factor, to a scaling factor of 1 over root 2. But it's reasonable to say, you know, what happens if you sort of not just dilating along a particular direction, but if you're dilating the whole body. And this sort of motivates the notion of total convex influence. So if you've got a symmetric convex set K, you can define the total convex influence as the rate of change of the volume of the set as you dilate it sort of uniformly along all directions. And it's easy to check that the total convex influence is nothing but the sum of the n coordinate influences. And if you write down the analytic expression, it's easy to see that this quantity is independent of your choice of bases. Or in other words, the total convex influence is rotationally invariant. As long as you pick any orthonormal basis, it remains unchanged. Again, in terms of pictures, the total convex influence is sort of the limit of the Gaussian volume of this light pink purple region divided by sort of this dilation factor delta up to a constant of 1 over root 2. And you might ask whether, you know, is this even sort of a reasonable notion of influence? Just as a sanity check, perhaps the first thing you'd want to know is whether the convex influence is non-negative. What are the possible values it can take? And if you think about the analogous notion of influence over the Boolean hypercube, the influence of a variable on a Boolean function is always between 0 and 1 because it's simply a probability. Yeah. And so it's natural to ask if this is true for convex influences, right? And if you think about this coordinate by coordinate, or this dilation definition of dilation characterization of convex influence, it's not immediately clear why the Gaussian measure of this dilate along a certain direction is more is bigger than the Gaussian measure of the original set. And as you can see from this image, when you sort of dilate along the first coordinate direction, the new set m sub delta k doesn't necessarily contain the original set. So it's not exactly clear why its Gaussian measure would be increasing. Also, in case it wasn't clear, if you could show that the Gaussian measure increases along dilations, then it would follow that the influence is non-negative, as the numerator in this fraction is always going to be greater than or equal to 0. But fortunately, or surprisingly, it turns out that these convex influences are indeed non-negative. And this sort of uses the fact that if you have a symmetric convex set K, and minus one dimensional, Gaussian measure of its cross sections is log concave. In particular, you can sort of express the Gaussian measure of the dilate in terms of an integral, which sort of uses the fact that the body is symmetric, and sort of log concavity implies that this n-1 dimensional measure is unimodal about the origin, which gives us the desired relationship, or which shows that the influence is non-negative. Awesome. So this tells us that the convex influence is non-negative. And the natural follow-up question perhaps is, what happens if the convex influence is precisely 0? So in the Boolean setting, if the influence of a particular coordinate on a function is 0, then the function is independent of that coordinate. Flipping the value of that coordinate never changes the value of the function. And something similar holds for convex influences. In particular, if the influence of a certain direction is 0, then the symmetric convex body K is essentially a cylinder along that direction up to a set of measure 0. Or in other words, it's sort of an n-1 dimensional convex body, which is just sort of a cylinder or just like translated along that direction. And so this seems to check out as well. So far it seems like, the convex influence is non-negative and it sort of behaves the way you would want it to when it's precisely 0. Another reasonable hope would be to sort of have analogs of some well-known standard Boolean functions and sort of see whether the convex influence of these analogous symmetric convex sets is sort of similar to the Boolean function, the influence of those Boolean functions. So perhaps one of the simplest Boolean functions are dictatorships, which are just the projection functions. So the dictatorship on the first coordinate simply takes in n bits and outputs the first bit. And it's easy to see that if you're the first coordinate, then you have influence 1 on this function. But if you're any other coordinate, then the influence is 0. And it turns out that the analogous symmetric convex body is simply a slab that's oriented along the first direction, along the first coordinate direction. So K is simply the set of points for which the first coordinate has absolute value, some constant, and it's sort of independent of all the other n coordinates. And the convex influence sort of behaves the way you would expect it to, and it's 0 for all these other coordinates. Another fundamental Boolean function is the majority function, which takes in n bits and outputs 1 if at least half the bits are 1. And the influence of each coordinate of the majority function is 1 over root n. And it turns out that the symmetric convex set, which is analogous to the majority function, is the ball of Gaussian volume half. So the majority function is sort of capturing the top half of the Boolean hypercube, and this ball of Gaussian volume half is sort of capturing the inner half of Gaussian space. And again, a calculation shows that the influence of each of any direction for this ball, just due to symmetry, is on the is 1 over root n up to constant factors. And finally, another sort of well-known famous Boolean function is the tribes function, which is an OR of a bunch of ANDs, and each AND is called a tribe. And this function outputs 1 if and only if at least one tribe is unanimous, or all the bits in a particular tribe are all 1. And this is sort of famous extremal Boolean function. And each influence of, and the influence of each coordinate on the tribes function is log n over n. And the analogous symmetric convex body here is the solid cube. So it's the set of points. It's a set of points for which each coordinate is at most root log n up to at most root log n in absolute value. And it turns out that the influence of each coordinate direction of the solid cube is on the order of log n over n. So far it seems like this notion of convex influence passes some really elementary sanity checks. But this correspondence seems to extend deeper. In particular, we are able to obtain analogs of some signature results from Boolean function analysis for this new notion of symmetric convex sets and convex influence for symmetric convex sets. In particular, we obtain an analog of the Poincare inequality, the KKL inequality, a sharp threshold result along the lines of Rieger-Klein, a robust density increment result along the lines of what O'Donnell and Wimmer obtained a few years ago, and a weak Friedgut-Hunter theorem, was sort of a consequence of Friedgut-Hunter theorem. And I just want to emphasize that the proof techniques that we use here are completely different from the techniques used to prove the corresponding statements over the Boolean hypercube. And I'm going to spend the next few minutes sort of briefly and at a very high level sketching the proof of the KKL analog. So just to remind everyone, the KKL theorem of the Boolean hypercube says that if a function has, if each coordinate has very small influence on a function, or more concretely, if the influence of each coordinate on this function f is at most epsilon, then the total influence is at least log 1 over epsilon times the variance of the function. So in other words, if all the influences are small, then the total influence is still reasonably large. And this is sort of a celebrated, well-known result. And it sort of sharpens the Poincare inequality for Boolean functions. This inequality is also tight, and it's tight for the tribes function, which we saw a few slides ago, and its proof relies on hypercontractivity. And the analogous statement for symmetric convex sets turns out to be pretty much what you would expect. So if K is a symmetric convex set for which the influence of any direction on this set is at most epsilon, and we've got this additional condition that the variance of the set K is at least epsilon, then the total convex influence of the set K is at least the variance of the set K times the square root of log of the variance of the set divided by epsilon. So we've got this additional square root factor as opposed to the Boolean KKL theorem. And I'm going to sketch the proof at a very high level again, just to emphasize the fact that the techniques used to prove these statements for convex influences are very different from the techniques used to prove the analogous statements for Boolean functions, although the statements sort of look the same. In particular, the proof of this KKL theorem for symmetric convex sets avoids the use of hypercontractivity or the log-sub-11 inequality. So we start off with the dilation characterization of total influence, which, again, just to remind everyone, tells you how quickly the set grows, or how quickly the Gaussian measure of the set grows under dilations. And we then appeal to the Gaussian isoperimetric inequality to conclude that the total influence is at least the variance times the in radius of the set. And we sort of crucially use convexity and the hyperplane separation theorem here. And then we sort of focus on this in radius quantity and rely on a Braskamp-Lieb inequality due to Vempala, a Braskamp-Lieb type inequality due to Vempala, to conclude that the in radius is at least square root of the variance divided by epsilon. And putting these two things together gives you that the total influence is at least variance times square root log variance over epsilon. And as I just mentioned, this is sort of quadratically weaker than the KKL for Boolean functions, and a natural next direction would be to obtain a stronger KKL. And there's many other directions that you could take this notion of convex influences in. In particular, it's natural to hope for a Friedgut-Hunter analog for convex influences. It'd be very interesting to sort of think about algorithmic applications of this new notion of convex influence. And another sort of very interesting question would be to obtain a robust version of one of our earlier sanity checks for convex influence. So if you remember, we showed that if a direction has convex influence 0, then the set is a cylinder along that direction up to measure 0. And a robust version of the statement would be something along the lines of the following: if a direction has very small influence, then is the set close in some sense to a cylinder along that direction. So just to recap, we've got this new and exciting notion of convex influence for symmetric convex sets of a Gaussian space, and we are able to obtain analogs of some signature results from Boolean function analysis for this new notion of influence. And it seems like there's a lot of exciting new things to pursue here.